This conference will now be recorded.
Okay, so good morning everyone and welcome back to a fresh new session of the economic theory classes. And we were discussing about the basics of economics, and our objective over here was to understand the very basics of demand and supply. And when we started talking about demand and supply, one of the most basic assumption which comes to play over here is the assumption of the markets. And one of the important things that we saw over there was that how is it that these markets would kind of operate, right? So how is it that these markets would kind of operate, and how is it that this operation would kind of bring them into so equilibrium? So what is the role of the demand and the supply process functions in ensuring the equilibrium? And while we were talking about that, we saw that the way the perfectly competitive markets were structured, right? There were a large number of buyers and large number of sellers, and each of the single buyers or each of the single sellers had a very small small fraction of the demand to cater to, or a small supply to provide, right? So they had actually a very little control over the prices. It is not the behavior of one individual, but it is the behavior of the group which will determine the demand, which will determine the unique market price. And this was done by and it was believed to have been done by an arbitrator, which was called the invisible hand by Adam Smith, right? So so while we were discussing this, one of the important things that we saw was that there was no incentive for the individual, for one individual to unilaterally divert from the equilibrium price which the others were charging, because they would not be getting any additional payoff corresponding to that. So the market price, which is determined by the demand and the supply curve, is the Nash equilibrium price. So that price itself is the Nash. And what ensures this is that the excess and what ensures that this equilibrium is unique, stable, and sustainable. So one of the important which talks about its stability, right, is the Tatonma process. The Tatonma process, as we talk about, is nothing but it is the process which ensures that every time the equilibrium is moved from that point, it always comes back and converges back to the same equilibrium point, assuming everything else remains unchanged, right? So that is one of the important points that we had looked into. Now the next question that came out over here is, or the next question from where we started that we should start our discussion is that how is it that this supply curve is created? How is it that this demand curve is created? When we say a supply curve is positively sloped, what do we mean? So how is it that I'm getting that the supply curve is positively sloped, right? So how am I doing this? So this is something that we need to talk about. That is something we need to reiterate. We need to create these fundamental curves. We need to derive these fundamental graphs, right? And as a result, what we also need to show is we need to show that it is these optimization behavior of these basic economic agents, like the consumer and the producer, which leads us to the market equilibrium. So we need to start from the consumer level or from the producer, and from the producer level, and derive these two respective curves. So what we need to do is we need to derive a relationship between the price of the price of an output and quantity of an output from the producer side and from the consumer side. So first, what we would do is we start off with the producer side, and what we would try to develop is the supply curve of the producer, right? Now, one thing that we know with any producer is that a producer, as we had already talked about, is a profit maximizer. So what are the incentives of a producer in a market? So let's first try to understand the producer's optimization, a producer's incentives. Then we will gradually kind of start moving into understand what exactly are the properties, and how does that hold in today's world, whether it holds in today's world or not, and all those and all the required features, right? So over here, what we talk about is just the producer's incentive. Now, when I talk about the producer's incentive, so first let's lay down the producer's incentives. Now, one of the most important producers and one of the most classically believed producers' incentives is nothing but the profit maximization. And this is believed to be and this is which yields the supply curve, right? So it is profit maximization. The profit maximization. Now, when we have this profit maximization, the second set of objective that they have over here is the output maximization. The second is output maximization. And the third that we have over here is cost minimization. Now, apart from that, there are also other objectives like revenue maximization objectives of the firm and so on. But we'll talk about them at a much later stage. So over here, what you have is cost minimization. Now, when I say that it's so these are the three objectives. Now, one thing that you will observe over here is that these two problems, profit maximization and the cost minimization, are the dual of each other. So they share a kind of a primal and a dual problem relationship. They have a primal dual kind of a framework. Okay. Now, one of the important things that we need to understand over here again, that so we have a primal. So what do I mean by a primal and a dual problem? So what it means is that if on one side I'm trying to maximize the profit, on the other hand, what I'm essentially doing is I am minimizing the cost, right? So these are the two. These two problems are the two sides of the same coin. So while I'm trying to choose that revenue to be the highest, I choose a X, which maximize my revenue. At the same time, I'm choosing that revenue such that it minimizes the cost, such that the gap between the two is maximized, and it is only then that the pi x is maximized. So the X star that would solve the profit maximization problem of a producer must choose the revenue at the maximum possible point and must minimize the cost at that point. So your cost has to be the minimum corresponding to that level of output, right? So this is how your supply curve, this is how you can actually solve your profit maximization problem. Now, what is the profit maximization problem over here? The profit maximization problem over here is very simple. So it is pi x, which is the profit, right? The profit function, and this function is the function. It is defined as the function of the revenue and the cost. So it is a difference of the revenue function and the cost function. So let's say the profit function that I have over here is pi x. Now this pi x is a difference between two functions. One is the revenue of x, minus the cost x. Right. So it is the difference between the revenue and the cost. Now when I say it is the difference between the revenue and the cost, so my objective over here is to choose an x star such that such that two things happen simultaneously at that instant. The one, so this revenue is maximized, right? So what we need to do is we need to choose that X star such that the revenue is maximized and the cost is, so it is only then that the gap will be the highest between the two and the profit will be maximized. So over here we deploy the first order and the second order conditions of profit maximization, and from there what we try to identify is that level of output which will maximize the profit of the function, right? Okay, so before we move into this maximization and the minimization, very quickly what we will do is we will recap, or we'll do a very quick recap on the first order and the second order conditions of maximization. The first order condition and the the first order condition and the second order condition of maximization, right? Okay, just look through this. We'll just get started in a minute. So let us first of all look into the first order condition and the second order condition. So what does the first order condition of maximization say? The first order condition of maximization says that the first order condition has to be equal to 0 and the second order condition has to be less than 0. So what does that intuitively mean? Okay. So let us first start off with that particular part. So let's say I have a function like y is equal to f of x, and this function is assumed to be both continuous function and differentiable over the entire real line, right? So this function is defined for the entire real line. X belongs to minus infinity to plus infinity, right? So x is defined over the entire real line, and hence x is y equal to be continuous and differentiable. It will be continuous So you have continuous and differentiable functions. Now the next question that comes out over here is that if I have a continuous and differentiable function, then how do I estimate my maximum and the minimum? Now to capture this maximum and the minimum, so let us very quickly draw a graph. So over here what we have is 0, we have x, and over here you have fx, or you have your y. So now the next question that comes out over here is that how would a function look like if it is a maximum? So let's take a color, another color. So a function which is maximum will gradually rise to a peak, and it will gradually fall down, right? So then you say that the function has reached a maximum at x star. So basically, to find out a maximum or a minimum, you first need to find out a point of optimum. Once you have that point of optimum, the next thing that you do is you tend to do this. This. So what I have over here is that the first point that you need to have when you're trying to maximize a function is you need to reach a point of invariance. You need to reach a point where the function is no more changing with respect to changes in x. And that's where you touch your point of invariance, or you come to a point where your dy or dfx dx is equal to 0. Now, after that point, if you try to increase x, right, the y instead of rising will fall, because y cannot reach to that point as it has already reached. It has this is maximum. So that therefore, from that point onwards, any additional increase in the any additional increases in x will cause the fx to fall, and hence the direction of the slope, I mean the second order derivative for a maximum function, for a function to attain its maximum, is negative, right? So the first order condition is 0. So you reach a point of invariance, and to check whether that point of invariance is a maximum or not, what you do is you look into whether the function is a negatively sloped function or not. So whether the second order derivative is negative or not, right? Clear about this part? Any questions? Any questions up to this? But okay. Now the question that comes out is that for a maximum, is it always necessary to have these conditions? Let's say, so can you tell me what will be the maximum and minimum of this function? So let's say I have a function y equals to fx, right? Now, dy dx, let's say dy dx is negative. Let me put it like this. Let's say f dash x is negative. Let's say f dash x is less than 0. And yeah, so what will be the maximum or the minimum? So what will be the maximum or the minimum of this function? So does this function have a max or a min? Or is it possible to calculate out the maximum or the minimum of this particular function? Yes. So just take 2 minutes time to think about it and then we'll get started. So will this function have a max or a min? I'll put myself on mute for the next couple of minutes. You can take your time, think about it, and then we'll get. Yes, anyone. Just put in your ideas in the chat box. Maybe right, maybe wrong, that doesn't matter. Just put your ideas into the chat box. Okay, I'll give you the answer. Now this function will typically have a maximum. It will not have, or it may not have a minimum. So basically, if you think about it this way, so think about it this way. Now, this function will always have a maximum, but may or may not have a minimum, or it may not have that exact maximum or an exact minimum, but it can have an asymptotic maximum and minimum depending on the structure of the function. So let's say this is a linear function and it's a negatively sloped linear function. So it is something like this. So in such a case, if this is the equation, then your y equals to a minus x, right? So it is something like that. So when your y is 0, right, so you'll get a value. So when your x is 0, you'll get a value of y, and with every x the value of y will decrease, right? So therefore this function will obviously have one maximum. Now if this function is of the form x by a plus y by b equals to 1, then it will have both a maximum and a minimum. On the other hand, if this function is not a linear function but instead it's a curvilinear function, it can have, so it can have a maximum, and then it may not have a typical minimum. It can have an asymptotic minimum, or it can have both an asymptotic maximum and an asymptotic minimum. So it depends on the nature of the function, whether it would be whether it would have a minimum or a maximum, or it would have a asymptotic maximum minimum. But over here in this case you can see that this condition is not actually satisfying. Why? Because the maximum or the minimum over here occurs at the corner. So this characteristic is not a good. I mean the classical constraints of maximum and minimum, condition of maximum maximization is not a good representative of functions which tend to have corner solutions, right? So these are strictly for interior solutions, where your functions are strictly convex or concave. You tend to have a solution in the interior. It is then that this definition is that this condition of maximization and minimization holds good. However, if it happens at the corner, then it is not a very robust condition, right? And that is why you will always see that it says that x star, or your functions, the way your functions are actually constructed, right? The revenue function and the cost function. Therefore, they are either constructed as a concave function or they are constructed as a convex function. And out of them, you study the linear functions as an exception to the the revenue and the cost. I mean, as an exception to the concave or the convex functions, because with linearity being introduced into this, the first order, the classical first order, and the second order condition of maximization, or for that matter, cost minimization, actually goes for a toss, right? And so, if I'm trying to think about it in the neoclassical framework, and I'm trying to mathematically represent each of these problems, right? There, I need to have that assumption, which will be in sync with that of the assumptions under which the calculus conditions are, right? So this is the reason why, when in the most general construct of the revenue function, that you see it as being constructed as a concave function and the cost function being constructed as a concave function, as a convex function, right? So any questions up to this point? Now, this is the reason I actually spoke about this part here, because when whatever sum we get, we first start taking it up and start differentiating things. You should not be doing that. You first try to assess that what exactly is the shape of the revenue function and the cost function. Now, if that difference is there, I mean, if it is that the revenue function is concave and the cost function is convex, only then you know that this way of maximization would help. Else, it would really not be helping us much. Now, another problem with linear functions is that they are not differentiable up to the after first second order, right? In second order, they become zero. So generally, we would want our cost functions to be at least quadratic in nature, and our revenue functions should be similarly quadratic or cubic in nature. Otherwise, doing a first order and getting a second order derivative is not very it's not very probable. So generally, so therefore, when we talk about the constructing this Rx and the CXs, right, and when we try to develop this profit maximization constraint, right, profit maximization model. Now, one of the things that you remember is are the assumptions which we generally tend to have on this Rx and Cx. So what are the assumptions that we used to have on these two or on these two components, right? So on one hand, you had the revenue function Rx. So obviously one of the assumption was that it must be continuously differentiable. So you should be able to differentiate it up to any order. So that is how your cost structure must ideally look like. Right. So the revenue function and the cost function both must satisfy the assumption that at optimality at x star, right? So whatever the values are, when you have the functional forms, those functional forms must be well defined in the real lines, and they must be continuously differentiable, right? So this is something that we would have with us. Okay. So any questions up to this? Okay, so before I just go through this, just take a minute's time, sit through this, go through this entire discussion, kind of frame this in your mind, because the next part that I do will have a very deep uh, connection, or it will have a very deep impact of this discussion on the others. On the so these discussions are going to have a very significant impact on the next set of discussions. Just go through this for a minute's time, and then we'll again get started. Okay, fine. So now let's move on to the next part. Okay. So now, first of all, we need to understand that if I'm trying to maximize, or if I'm trying to create the, so you're trying to maximize the profit, right? So how is it that the profit maximization or the revenue curve and the cost curve should look like? Now, generally, what happens is the revenue function or the revenue curves are defined as the concave curves, right? So they are defined as the so they are mostly thought of as being a concave function. Is thought of as being a concave function because as the, the level of output rises, the growth in the revenue function is not as much. So the revenue function grows at a relatively lower rate than what the than what the level of output does. So the growth in the revenue after a point of time becomes less than proportionate as the output levels grow. So that is why the revenue function is often considered to be a concave function. Now, obviously, if you are actually defining it to be a concave function has to be kind of differentiable at least up to 2 to 3 orders. So mostly your cost functions are decided to be, your cost functions are revenue cost functions are mostly concave or convex in nature. The next part that I have over here is the cost function. Now the cost function that I have is a convex function. Now it is a convex function because it is believed that in the initial stages, or in the initial stage of production, the additional cost or the marginal cost of producing one unit is relatively lower than over successive levels. So after a point of time, the cost actually starts increasing because what happens is up to a certain point of time there is an efficiency of scale which operates, but after that the potential or the effectiveness of the process is lost. So if you, with a given plant size and with a given production capability, if you are trying to produce beyond a certain unit of output, then what happens is you start losing out on the efficiency of your losing out on the efficiency of your production exercises. Now, so therefore, one of the very important points that we have over here is to identify, or is to think about the fact that therefore, so after a point of time, if you have reached a maximum, or you reach an optimum point of your cost structure, from that point on the cost structure will start increasing, and when that happens, right, the revenue addition gradually starts becoming relatively lower because after a point of time what you are doing is you need to charge a relatively higher amount of price, and hence the demand actually starts falling. So therefore, the revenue gradually narrows, flattens out, and the cost structure gradually or increases steeply, and then the difference is kind of worked out. Now, given that that difference is kind of worked out, the next thing that we need to understand over here is that how whether it is a concave function or a convex. So given these two functions, we now need to identify that what is the point where the profit is maximized, right? So first we'll solve this profit maximization exercise mathematically, and then what we'll do is we will solve this result graphically as well, right? And from there, our objective will be to derive the supply curve. So the first order condition that we'll have over here is the following. Okay. So let's solve the first order condition. So it is d pi x. Okay, the first point that we have over here is that d pi x dx is equal to 0. So how do I solve this? So this is nothing but the first order derivative of revenue the sum. Okay. So over here what we have is over here we have dcx. Okay, so this is the DRX minus DRX DX minus DCX DX. So it says that the so when you're trying to maximize the profit, the marginal change in revenue must equal the marginal change in cost. And that is the point where my profit will get maximized. Right? So we can write this as at the point where d by x dx, so which is dcx dx. So it's so this equation clearly shows that it is the marginal revenue and the marginal cost, the points where the marginal revenue and the marginal cost is equal. So that is the point where the profit is maximized. So the first order condition for doing this is the marginal revenue is equal to the marginal cost. Right? So this is the profit maximization in detail. This is something that we have always learned in our economics days, so which we have already learned in our undergraduation days, right? R prime x equal to prime x, and you have this. Now the next question that comes out over here is, so now the next question that comes out here is that we have the so we have the R prime x, we have the C prime x, and so the point where the marginal revenue is equal to the marginal cost is what we choose for the profit maximizer, although the point where the profit becomes invariant. Right. Now, so that means what? So what does this marginal revenue equal to marginal cost mean? So graphically, if I have to represent this maximum, this marginal revenue equal to the marginal cost, one of the important things that we would kind of identify or that we can think of over here is, oh, so basically we try to optimize at a point where the slope of the revenue curve, okay. So it says that the slope of the revenue graph slope of the revenue curve must equal equal to the slope of the cost curve. So we have the slope of the cost curve equals to the slope of the revenue. Now the next question that comes out over here is that how do we do this graphical? So mathematically, this is how it appears to be. The next thing that we need to look in over here is that how do we do it graphically, right? And then we need to judge the second order condition, that what should be the sufficient condition for this maximization exercise to hold, right? And once we have this, then from there we will go ahead to derive the individual supply curve and we'll say why is it that the supply curve is always positive slope, and what are its further implications, right? Just have a look into this for a minute and then we'll get started. Okay, any questions up to this point? Fine. So let's try to plot this revenue function, and let's try to plot this the revenue function and the uh, cost function, and as a result of this, let's try to identify the profit maximization point. This is where the output is. We'll talk about a revenue function, and we'll talk about a cost function. So those are the functions which are plotted on the y-axis, and over here you have the x-axis, you have the outputs. So first what we'll do is we'll plot the revenue function. So I'll plot the revenue function in blue. So the revenue function will initially increase, after a point of time become flatter, uh, and start falling. So after a point of time, the total revenue that you have, or the revenue that you had actually had started growing, but then after a point it actually starts falling, right? Similarly, the cost function that you had, the cost function gradually starts rising. So basically what will happen is you gradually start, your costs gradually start increasing after a point of time, right? So this is your cost function, Cx. So this is your revenue function. Revenue function, right? Now the next part that we have from here, that we need to identify from here, is the point where the profit is maximized. Now the point where your profit maximizes, right, is something like this. So the functions, the slope of the function at that of the revenue curve and slope of the function at the cost curve will be more or less similar, and they will be, they'll more or less be flattened out, right? So something like this. And not because I'm drawing freehand, I'm not being able to kind of get it exactly. But this is the point where the maximization happens. Right. So this is the point where your R prime X is equal to C prime X. So when you actually compare them, you actually say, you can say that there is a point, but there is a level of output corresponding to which the profit maximizes over there, right? So you have this R prime X equal to C prime X criteria built over here. Now the next question that I have, so I have this point right now. How do I interpret this particular graph? So observe that in the lower levels of the output, so let's say over here, so over here, the consumer or the producer is producing this much. So this is the revenue that he is earning, and this is the amount that he is actually using. He's actually kind of spending to make that revenue. So he's earning a profit over there. Now the question is that an optimum point? Now the point, the question, the thing is that if he moves off from that point, does he come back again to that point? So that's something which is that is something which is important. So if there's a small increase in the cost and small increase in the revenue, so the profit that he makes, so will he come, will that profit be lower than this point, and will he come back to this point? So what we do is we diverge it by epsilon, right? So we kind of create a, so we just kind of increase the output by an epsilon and compute the cost. So one thing that you see is that this is how the cost is behaving over here, but the revenue here is this much. So over here, the output is increasing much more so than the cost. So the cost per unit of the output is not increasing very quickly. So the marginal cost at this stage is actually falling. So if you look into the marginal cost structure of the farm, the marginal cost over the levels of initial level of output is falling. Why is it falling? Because over here the farm has started its production. The production that the farm is doing is much below its overall capacity, and it has still an excess capacity to be utilized, right? And hence what you see is that as you move from one point to another, the marginal cost, total cost increases, but it is less than proportionate to the increase in the output. That is, the additional cost of producing a good gradually goes down, right? And it starts keep on going down up to a point, right? So the producer will earn a greater profit by shifting from that point to the next point. Now similarly, when you see a producer is increasing his production further, he further increases his production again. So do you have an incentive to go back to the last profit? No. So that means this is a permanent divergence, and this becomes a new equilibrium. Now is this equilibrium sustainable, or is it actually equilibrium? So what I do is I say that no, if I increase my production further, I'll make a greater profit, right? So over here again you see that this is how the cost, the production, the marginal cost is, and this is what the marginal revenue is, and this is what the structure is. So what happens over here is, so over here what we see is that this keeps on gradually increasing, and at each stage the revenue, the profit that the farm is making is increasing, right? Now what happens is, assume that the farm is here, the farm is here. So now you see that the increase in the marginal cost is, so the total production now increases rapidly, right? And the revenue is increasing less than proportionate. So now there is a point where the farm is coming to terms and is kind of coming to stop its production. So similarly, the moment the farm ventures into this zone, the farm sees its profit falling. So this profit, so this is pi of x star. This is pi of x star, right? So the relationship that happens or that holds over here. So if you either, if you isolate the relationship that is holding over here between these 3 points, it is something like this. Profit So I have this. So similarly, pi of x star will be again greater than, right. So this is where the profit has been maximized. Now, if the firm starts going further, what will happen? The revenues will start falling and the cost will start increasing. And as a result, this zone becomes the infeasible zone of production. So this zone is an infeasible zone of production. Now, for a reference on this, you can read up the production theory book on so written by Ryan and Pierce. So over there, when they talk about the producer's maximization, they talk about this part. So it's so this the explanation that I've built up over here is in reference to Ryan and Pierce. So you can have a read over there, right? So over here, this is your infeasible zone of production. So this is your infeasible zone of production. You have your invisible zone of production. Now, one of the important things that we have when you talk about the invisible zone of production is this product over here, either the farm is reducing its profit or is kind of earning losses. So when you see the cost has exceeded the revenue and they have kind of cut, so that's the point where the firm has started earning losses. So this is the zero profit point. So this level of output is the point of zero profit. And over there at zero, there is a zero profit. So this is precisely how the the profit maximization condition is identified. Now, what actually then ensures that this point where the slopes are equal, that the what ensures that the profit is getting actually getting maximized at that point. So, what ensures that the profit is getting maximized at that point is the fact that the marginal cost curve, marginal cost starts increasing from this particular point. So it says that the marginal cost must be upward rising, right? So over here, one of the important observations that we get to see is that one of the important observations that we kind of get to see over here is that the necessary condition for optimization is for the profit maximization is that this function must or the marginal cost curve must be positively sloped. So let's say if you have a look into this part, right? So let's say r prime x. So this is the second order derivative, right? So let's say when the second order derivative is zero, so we assume a linear revenue function because it's a perfectly competitive market and the prices are given, so therefore r double is zero. So one of the things that we can say over here is that for d2 pi, now for d2 by dx2, what we need to do over here is we need to calculate. Mhm. So r double prime x. Now over here r double prime x is here so because it's a linear function because it's a perfectly competitive market. Therefore r prime x is constant and r double prime x is zero, right? So what it means is it should be minus c prime x, c double prime x should be less than 0. So what this means is c double prime x should be greater than 0. So c double prime x is nothing but dx, it is ddx. So it shows that the second order condition over here shows that as x increases, the marginal cost must increase. Right? So it is in this region of increasing marginal cost that the profit will get maximized. So if the profit is getting maximized, the first condition that must hold over here is that you must have the marginal cost equal to marginal price, and the marginal cost of the firm, marginal cost curve of the firm must be rising at that scale. If not, then that's not the profit maximizing point. So MR equal to MC can happen at multiple points, but it is only when it happens at the point above the marginal, where the marginal cost curve is rising, only then can you say that yes, this is a proper marginal cost curve. I mean, that's the proper profit maximization point, right? So we will talk about the profit maximization from that perspective in the next discussion. So from today's discussion, we have identified the criteria for the profit maximization. What is the total revenue curve, cost curve? How is profit maximized? Now from this total cost curve that we have constructed over here, we'll intuitively start constructing the average cost curve and the marginal cost curve for the firm, and from there we'll kind of try to find out the profit maximization and hence the supply, right? So with that we will be completing the discussion on the supply curve for the producers, right? So we'll continue with the producers optimization tomorrow, and we'll end with constructing the supply curve in tomorrow's discussion, right? So your recordings so 2 recordings have already been uploaded in the YouTube channel. The remaining 2 recordings, last week's class and this class, I'll be uploading in the YouTube channel. So we will override this explanation will override the explanation that we did in the last class, right? So we will be focusing on the explanation that we did over here, and that will kind of form the continuous chain. So you can go through those 4 recordings, and from there we will take it up, and tomorrow we'll have the 5th recording. So by Monday you will have all the 5 recordings on the YouTube channel, right? So thank you for your time, guys. Thank you for your time, and let's catch up tomorrow to finish off this particular session. And if you have any questions, queries, do write the mail to me, or do reach out to me through my handle. Thanks a lot.